Today, we're going to give a small introduction to Coulombs Law, and we're going to be using a simplified version of it that does not include the constant. Alright, the constant is real, we should include it if we're doing very serious math, but the law we're going to talk about today is only to be used relatively to compare different elements and compare different forces of attraction. First, let's break down what Coulombs Law says. Coulombs Law is this. F equals Q1 times Q2 divided by D squared. F is the attractive force between two oppositely charged particles. Q1 is the magnitude of that positive charge. So magnitude here means absolute value. Positive charges are already positive, so we can just report the number, right? If the positive charge is 2, we're going to write 2 for Q1. Q2 is the magnitude of the negative charge. So we're going to write all these numbers with no negative sign because magnitude means absolute value. Then finally, D, distance, is the number of energy levels between the positive and negative numbers, positive and negative charges. So let's do an example with lithium. All right, lithium, if we're thinking about just the atom, looks like this in a Bohr model. And let's try to calculate the attractive force that's felt between the nucleus of lithium and this valence electron. If we're going to do that, we have to know the positive charge is the effective nuclear charge. It's the positive charge from lithium that is felt by this valence electron, which is 1. Lithium has a Zeph of +1. Electrons always just have a charge of -1. So whenever you're doing this math and you're talking about single atoms, you're just going to plug in 1 for Q2. And then for distance, it's the number of energy levels from the nucleus to the electron that we're talking about. In this case, there's 1, 2. And we get a number that is 1/4. This number 1/4 does not mean anything by itself, but it does mean something when we compare it to other atoms. So let's do the same process for fluorine. Fluorine looks very similar to lithium, except it has 7 valence electrons. So let's think about this. The Zeph of fluorine is 7. The charge of an electron is still just 1, and there are still 2 energy levels. Now, this 7/4 again by itself is meaningless, but when compared to the answer for lithium, we see that this is greater. And how we interpret this, we would say that the valence electrons in fluorine experience a higher attractive force to the nucleus than those in lithium. After we do this math, we can only make these types of general statements. All right, we cannot say exactly how much bigger, we just know that it is a bigger attractive force. All right, tune into future videos where I'm going to get more in depth with Coulomb's Law. All right, but I am going to assume you understand what it is and what those variables stand for.